So let's draw now properly in the TF diagram the ideal vapor compression cycle once we have explained the different components that we have. So here this cycle is made of 4 different transformations. First, a compressor, and this one can usually be taken as being adiabatic, and here we also consider that it is reversible, so from A to B, and this will need to be completely in vapor phase. Then we have a heat exchanger called the condenser, in which the fluid is cooled down to saturation and then completely condensed by giving heat to the hot source. Third transformation, we have the expansion valve from C to D, and in that case we have an isenthalpic expansion because there's no technical work and no heat exchange. And finally, from D to A, D is already two-phase at low pressure, and there's an isobaric heat exchange with the cold source, where it's receiving heat from the cold source, and the working fluid is evaporating completely up to A. So first thing we can note is that we have 2 characteristic pressure in this machine, because we have 2 devices that are changing the pressure, the expansion valve and the compressor. And so here we can write the high pressure level and here the low pressure level. On the TF diagram, what I suggest is first plotting the 4 characteristic temperatures that we have. So, because we are exchanging heat with sources, we can first write the T cold temperature of the cold source and T hot the temperature of the hot source. But we know also that we have a condensation temperature which is higher than T hot, and we have an evaporation temperature which is lower than T cold, T evap. The 2 different pressure levels correspond to the saturation pressure relative to the phase change temperatures in order for this the phase change to take place at these temperatures. So here we can draw schematically the isobaric line that are merged with these temperatures inside the 2-phase zone. So for the low pressure, it will be like this, and for the high pressure to be like this. So that's it. Now let's start plotting where the different points can be met. Let's start with point A, the inlet of the compressor. Point A is at low pressure, so that's low pressure, that's high pressure, and point A needs to be completely gaseous, so in the vapor zone. So in that case, at first approximation, we will just put A just at the smallest entropy that is on this isobaric line, but in the vapor zone, so just as saturated vapor for point A. Then from A to B we have compression, and if we can consider the compression as being adiabatic and reversible. Adiabatic, there's no entropy exchange. Reversible, there's no entropy creation, so it would be an isentropic transformation. So the entropy of point B will be the same than point A. So this specific entropy can be plugged this way. Of course, the isentropic lines are vertical because it's the x-axis, and point B will be at the high pressure and on this isoentropy line. Then from B to C, it's an isobaric heat exchange. So the fluid will give heat to the hot source through the heat exchanger, and this will lead to cooling down from point B to the saturation temperature, and then once it's saturated, the temperature will not change anymore, but instead the working fluid will be condensed up to being saturated liquid. So at first approximation, it is usually considered that C at the outlet of the condenser is a saturated liquid when C is there. Then from C to D, we know that D will be at the low pressure, so on this isobaric line, and it will be at the same specific enthalpy than point C. So then we can look for the isoenthalpy line that is crossing point C, and it will have a shape like this. So that's the specific enthalpy of point C, and at the crossing with the low pressure, that's the point D. And then in the evaporator, there's again an isobaric heat exchange from D to A, and the fluid that started to evaporate inside the expansion valve will finish evaporating until it is saturated vapor in point A. So that's what will take place inside an ideal vapor compression cycle, represented in a TS diagram.